Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's Semester 2, 2021, and this is a revision seminar for Mathematical Economics 1. And I've had some requests about integration, so I'll start with that. And if there's time later, we'll talk about some other things too. So that was for your benefit, people who are watching this in the future. Hello from the past. Let's just start. All right. So the first thing I want to say is that integration is designed to accumulate quantities across space or time. So the idea is that there may be a line, and then traditionally you would have a position on the line located by numbers. And if you've attached a number, a new number to every position on the line, so in a physics sense, maybe it's a temperature, or maybe it's a electrical field potential, which is what, you know, this is all designed for physics originally. But in an economic sense, it may be the rate of change of the utility of something, or whatever. Like it could be anything. And there's a number at every position. The idea is to, as you move from one spot to another, to sort of accumulate all that crap and see what it adds up to. But what you want to make sure, to do is to make sure you take into account that if the answer number is the same, happens more often, then it's included more often. That's what you want to do. So, and it's designed, one of its original purposes is to average things. So, you know, when you do an average, you add them up and you divide by how much there is. Imagine this thing. So I'm just going to draw something. It's like 10 here, and it's 2. Yeah, I'm going to say 0. It's 10 here and it's 0 here, right? So just don't step back. The number that's attached to everything, you normally draw it as a height in a graph. Classic, right? So if you've got something that's 10 for a bit, like from 0 to 5, and then it's 0 from like 5 to 15, the average height should be sort of closer to 0 than it is to 10, because it spends more time being 0. That's the basic idea. And so what you do is, if you want to figure out the average, you go, well, it spent 15, that's not 15. Yeah, it spent 15 amount of time, right? So you have something divided by 15, and then across that time it spent 5 minutes being 10, and then 10 minutes being 0, because this is 10 minutes here. And so that would be the average. That's the basic idea of how integration works, of what it's trying to do. And so this bit here, that's the integral. The bit where you're doing the adding up, where you're including a number based on how much space it takes up, how much time or space it spends being that number. And so it was originally, like, the theory of integration is based on things that are flat like this. And this is actually the reason why integrals are allowed to be negative, because a negative, if you had something that was like this, that spent some time being 10 and some time being minus 20, then on average, you'd expect it to be, the average would be like here, which would be negative. So you need integrals to be allowed to be coming out to negative. And so you go this, it spends this much time being 10. So when you go 10 times this, you'll get 10 times this, you'll get an area. And it spends this much time being 20, and 10, this times minus 20 is this area. And you need this area to count as negative, so that when you add them together, the average ends up being negative. So areas that are below the x-axis have to be negative in order for the whole idea of averaging things that are positive and negative to work. How do you feel about all of that? Okay. And so The problem is when it's curved, it's not nearly so easy to figure out what to do. But we have an answer. When it's flat, it's an area. So when it's curved, it will also be an area. And we also think that when it's curved, we could cut it into pieces that are really tiny. And if they're flat, little tiny flat bits, then when I do lots of little tiny rectangles, it should come out to approximately the correct amount. Yeah. Ultimately, what we're actually doing is trying to fit it between some things. So if I had something like this, I'm not going to do a positive and negative one. I'm just going to do one that's positive. I would know, so I could cut this into whatever pieces I wanted and say, on this bit, this is the lowest amount here. And so if it was equal to that lowest amount all the way along, this would be the area. And this is the highest amount. If it was equal to the highest amount all the way along, that would be the area. And so the true area for that bit must be somewhere in between this and this top area and this bottom area. And if you do it on every interval, you'll get this bottom area. And you say, whatever the true area is, it's got to be between, it's got to be less than that bit and more than that bit and less than this bit. And if you make all these intervals narrow enough, those two answers are going to be really close together and they must be close to whatever the real area is. That's the theory behind how mathematicians define what area really is for curved objects. How are you feeling about that? How are you feeling about that? Okay. I mean, ultimately, this is the theory behind it. And so I don't think it will turn up in your exam. Not that everything in life is about exams, but for these 2 weeks it is. I guess since it's a curve, we can believe that the area is really there, which is what we're trying to get at. But believing that it's there is not the same as feeling comfortable mathematically that it's really a number that actually exists. And so if I just do like a piece of a circle like that, I know the area of a quarter of a circle because it's been known since ancient times. But what if I didn't believe that it had, like, what if I really wanted to believe that it was possible to absolutely have a single number that describes this area? I would have to convince myself that it really did work. So sort of just stop. What if there was no formula for the area of a circle and all I had was a formula that told me how high this was, which is this formula. So what if all I had was this, but I didn't have the formula for the area of a circle? How would I go about figuring out this area? You go, I don't know, but I do know the area of a rectangle. So I know that this area, whatever it is definitely less than 1 times 1 because of that rectangle. And I also know that this area, whatever it is definitely more than this. So whatever the area is, it's definitely more than like a half times a half, which is a quarter. And that's the thinking that I'm going to use. I'm going to cut it into pieces and try and figure out that it's less than something or more than something. So if instead I cut it into, it's not actually at a, no, it is a, just give me a second. I'm feeling uncomfortable about something, so I just need to worry about it for a sec. This is perfectly symmetrical, right? So that should go through the side. Yeah, this is not a half and a half. That that middle point there doesn't happen at a half here. It's closer to this end than that end. Crap, it happens at 1 on root 2 times 1 on root 2, which is a half. Okay, because of pi trigonometry. But if I cut it into, say, 3 pieces, then I would know that it's that this rectangle and this rectangle and this rectangle, those 3 rectangles, the area's got to be less than them. So the true area is less than whatever those 3 rectangles add up to. Yeah. But it's got to be more. It's got to be more than this rectangle and this rectangle because those are sitting underneath it. Than these 2 black rectangles, right? Those 2 black rectangles are underneath it and they've got to be less than the actual area. And so if I keep slicing it to thinner and thinner pieces, the collection of all the rectangles that are too high, that area, and the collection of the rectangles that are too low, that area, they'll get closer and closer to each other. And they must get closer to whatever the actual area is. And that's how mathematicians define what the integral number, the definite integral number actually is. Yeah. But technically it doesn't matter how wide the slices are, like you're allowed to have them all different widths. Any width you choose, you can choose different, any width you choose, you can put the biggest rectangle that sits on that width underneath the curve and say, well, the area's got to be bigger than that. And so what you do is you go, if there really is an area, it has to be lower than any of the top collections of rectangles. Like if any collection of rectangles you have that's too high, it's got to be less than that. Any collection of rectangles that's too low, it's got to be higher than that. And as any number that's less than all the upper ones and more than all the lower ones, there's only going to be one number that does that. And that's the actual area. Feeling a bit better about it? Yeah. So that's the theory. But over in Maths 1A that they do in the Maths and Engineering degrees, they actually have to do calculations with the little areas, little rectangles. But as far as we can tell, you don't. So that's great. All that theory about the rectangles and stuff, that didn't come into play until like a couple of 100 years after integration was invented. When Newton sort of invented integration, he noticed that when you did, he noticed this. If you have a function like x, y equals x, it's a perfectly good straight line, then when you start here and do a running total of the area so far, that's what I'm going to do. So this is position x, and this is the area so far. So that as the x moves, the area keeps getting bigger and bigger, right? Then that area so far, well, it's x wide, and this is y equals x, so it's also x high, because that's the height, y equals x. And it's a triangle, so it must be a half times the base times the height, which is a half of x squared. So that function of the area so far is half of x squared. And what Newton noticed is that the derivative of this is that. So when you do the derivative of half of x squared, you'll get a half times 2x, which is x. So the area on dx comes out to this, which is what I started with as my function. And he noticed that that always works. Isn't that cool? Yeah. I mean, he didn't just do it for this one. And we don't really know. I mean, he wrote a giant book on it, but in Latin. So, you know, because back in those days, if you did science, you had to do it in Latin. So, yeah. And I don't know when the notation, like a lot of this stuff, they were still figuring out how to do maths notation. And so, yeah, I don't know where that is in the sequence of things. So That's the fundamental theorem of calculus. There are actually two fundamental theorems of calculus. So one of them says that if you do a running total area function, you start with a function and then you make a new function that's a running total area, then the derivative of that will be the function you first thought of. That's one of the fundamental theorems of calculus. And the other fundamental theorem of calculus is if you want to figure out an area, then you have to anti-differentiate something and subtract the two pieces, which is the one that's in your notes, I think. Yeah. So your fundamental theorem of calculus is essentially just how to do integrals. Okay. So overall, the message is that the point of integration was to accumulate quantities. You know, if you've got something that keeps flowing in and flowing out, you sort of want to add them all up and then you'll get a total amount at the end. And those quantities can be represented as areas. And it's all about areas, which is what a definite integral is about. So a definite integral is you've got a function and you have positions on the x-axis, which will be whatever they are. I'm just making up stuff. Then this area is denoted by the integral from 2 to 5 of f of x dx. And the reason it's a dx is because what we're imagining is all of those little rectangles. If I slice, I know that one of the reasons why these integrals are the way they are is that we're slicing up this thing into a whole lot of really thin rectangles. The height of that rectangle is approximately the current function value because that's how you do the height in functions. And the width is an extremely small change in x, which is what the dx stands for. And so this little teeny tiny skinny area is the f of x times dx, and then we're adding them all up. And this stands for, is an S for sum. Yeah. It's a very stretchy, smooth S because there's infinitely many of them. As opposed to the kinky S, which is a capital sigma, which is the traditional word symbol for sum. This one's smooth and this one's clunky. So anyway, that's the difference between them. Yeah, but I don't think about it as that. It's like I'm accumulating values of this across this distance. So that's that. That's a definite integral. And if you draw it as draw a graph, then it will be the area counting the areas below as negative. Yeah, feeling okay? The indefinite integral has two lives. One of the lives is if you pick any function and you pick a starting position and you make a new function, which is the running total area, like what the area is so far, starting at A and moving forwards. This is the area at. So I'm going to call it the area so far at position X, right? That's a function of X. Different X's will give you a different area so far. So if you look at the area so far of X is going to be the integral from A up to X of f of something d something, but it confuses people if you use an X in the top and down the bottom here. So I'm going to call it T if that's okay. So this axis is T and one of the choices for T is X. Yeah. So what Newton discovered is that area so far functions, when you differentiate them, so this is supposed to be a little f. Area so far functions, when you differentiate them, they give you the original function back. Very cool. But that's the reason that is that the tiny differentiation is about how much extra you get for going over a little bit. And the amount of extra area you get for going over a little bit is this high. F of x high, and that's why the derivative works that way, which is really cool. Like, it's just so clever. So this is a function of x. And so it must be integrals, and choosing different starting points will give you different functions. If I started here, all the answers would be this much bigger. And if I started here, all the answers would be this much smaller. And just so you know, if you run it backwards, then the answer comes out to be negative as well. So if you run your integral in the wrong direction, like from 3 to 2, then the answer comes out to be negative. Because you're still accumulating, you're just accumulating backwards. And so it should come out to be minus what it was if you accumulated forwards. So because starting at different positions gives you different answers, and the difference between them is a constant bit of area, when we don't have numbers on these, we put a plus C. Yeah, because if you knew where it started, you would know what the C was that made it different from the other one. That's one reason. The other reason is just from a straight up algebra perspective, is that we know definitely that whatever this function is, the derivative of that function is this. And so I know that if I differentiate something that's got a constant on the end, the constant disappears. And so I have to, if I want to cover all the possibilities, you've got to chuck a constant on the end. So that's 2 reasons why you have that plus C. How are you going? Does that add anything to what you already understood? What?
Or just the history.
Yeah. I mean, I might have mangled it a bit, like I don't necessarily have it in the right order, but yeah. Integration was discovered and differentiation were discovered independently, and they later discovered they were related. So, yeah. Because, I mean, they're really not, when you look at areas and slopes, you're going, what? I mean, to be fair, if the steeper this is, the faster this area is going to go up. And so it's not very far from knowing that they must be related in some way, but how they're related is a bit difficult to process. And so, you know, Newton and Leibniz were pretty clever to figure that out. Yeah. Okay, so that's the theory. What that means is, in order to calculate a definite integral, what I need to do is figure out what differentiates to produce my function. Right. And they, over in, you know, many maths courses in schools and universities, they call that anti-differentiation, because you're doing differentiation backwards. Cool. So now we're going to have some techniques of doing integrals. So the techniques of integration in general are designed for finding wait. This is called an indefinite integral. Because there's no particular reference to where it is on the number line. So there's no reference to which zone you're adding up across. And so that's why it's indefinite, because we don't know, there's no definite information about where it really is. But in the back of your mind, it's always about definite integrals. Even these are, because this is just a possible answer for what the running total is from a definite integral. Okay, sweet. So techniques of integration generally go with indefinite integrals, and you just use them to find the correct formula that goes in your definite integral spot when you calculate it. So we'll do that in a minute. Oh, wait. Not there yet. One more thing. So if you want to figure out what this area is, and you know that the running total area function is one of the antiderivatives of this function, of the y equals f of x, that's what we know from the fundamental theorem of calculus, that the derivative of the area so far is that. So if I find an antiderivative, I need to draw just a second. So here's 3, and here's 5, and I've got my function, and I want to know the area from 3 to 5, say. Okay? integral from 3 to 5 of f of x dx. I know that the running total area function, starting at 3, for example, will be an antiderivative of this. So if I find an antiderivative, which I shall call capital F, right? I know that my antiderivatives in general are all running total area functions. So all my antiderivatives, it's probably not true that they all are, but close enough. My antiderivatives are going to be a running total area function. It's just that I don't exactly know where the start of that running total is. So if I choose an antiderivative, I know that this is a running total area starting somewhere, but I don't know where, right? So if I did the running total area from that starting point up to 5, minus the running total area from that starting point up to 3, then that would leave the bit from 3 to 5. Ta-da! So this is a running total area. Running total from here to 5 minus the running total from here to 3 should leave the bit from 3 to 5. And that's why this theorem works the way it does. So it doesn't matter which starting point this running total area has, it'll always work out to the same answer if you subtract the 2 bits. How are you feeling? Yeah, it's exactly the same idea of doing things with probability distributions. So when you're doing like a normal distribution, you want the bit between here and here, you go everything below this minus everything below this, which is really your running total area from minus infinity up to here. And from minus infinity up to here, and you take that off and ta-da, it's the bit in the middle. And so actually, I mean, when you're doing probability distributions in the mathematical theory, it's integration because it's areas. So in a probability theory course, you'll spend a lot of time integrating stuff, like in the first few weeks, because that's what it's all about. Very frustrating for mathematicians because the curve, the normal distribution curve, this thing here, you know, that thing, it's like y equals like 1 over root crap e to the minus something squared or whatever. There is no formula for its integral. It totally has an area, but when you do the integral of that dx, and you know there's an answer plus c, this answer cannot be written in terms of powers of x and e to the x of square roots or ln's or any of those things. It's impossible to write a formula for that in terms of functions that we know the names of, which is really frustrating. So the only way to do it is to cut it into a whole lot of little rectangles and literally add them up, which is why there exists things like normal tables. Because back before we had computers that held all that information, they just had to painstakingly actually do all the little areas and add them up and then write down that the running total area up to this bit is 0.135, whatever. But because there's no formula for it, that's the only way. Yeah, so that's the most frustrating piece of calculus in the universe, is that the normal distribution doesn't have a formula for its area. Yeah. There you go. There's some pretty good approximate formulas, but there's no exact formula. But luckily, there are lots of functions that do have formulas for their integrals. So these are the techniques of integration in the order of easiness, right? In the order that you should try them. So technique 0 is just do it, because you already know the answer. All right, I will describe what they are in a minute. And under just do it, there is like, you know the answer already. And there's another technique which I will list in a minute. And technique 1 is rewrite it. Meaning that all you might have to do is like expand the multiplications or factorize or something, and suddenly you'll know what to do. Because sometimes it's not difficult to do after that. Technique 2 is substitution, which your lecturer calls change of variables. And then technique 3 is integration by parts. And if you did a course that was only on integration, there's a few specialized techniques that come after that, but they're not in your course, so we won't cover them. But the other specialized techniques are usually just fancy ways of rewriting things or fancy ways of doing substitution. So yeah, they are the techniques, and that's pretty much it. And the best way to decide which one it is to run through the list and think in your head, will that work? Probably, let's give it a go. Or will that work? Nah. Will that work? Nah. That work? Nah. That one, that's the one that's going to work. And that's true of any time when you get given a lot of techniques and you don't know how to choose between them, then look at them and put them in order of easiest to achieve the answer and run through the list. Okay. All right, here we go. So with the just do it, you know the answer because you know your derivatives. And so it's not just know the answer, it's like no derivatives. So on the list of just do it is all the things that you know the derivative of, which are, as far as I can tell me if I'm wrong, if you have a power of x, I hate writing this as a formula. I really hate writing this as a formula. But if you have x to the power of some number, then when you integrate it, so I'm not going to write integral signs, I'm just going to write int. When you integrate it, what you'll do is you'll add 1 to the power, add 1 to the exponent and divide by the new exponent. So I hate this formula because it doesn't look like what I'm doing in my head. So I'm going +1 to the exponent and divide by the new exponent. An exponent is the fancy word for what goes in this position, because technically power is the answer you get at the end. So just in case you're wondering why I'm not saying power. Okay, and this will work as long as you don't have to divide by 0. So it's not going to work for x to the power of -1. Sadly. But that's okay. That's got its own rule. 1 over x, which is the same as x to the power of -1, will integrate to give ln of x. Does your lecturer write it as ln? Many places in the world pronounce it as ln, especially in most of Asia. Maybe not Russia. Most of Asia south of Russia will pronounce it as ln. It is not an I, it is an L. It's a small L. Lots of people who learn this for the first time and only learn it from reading think this is an I, a capital I. And then when they enter something into the computer, it goes, I don't know what you mean. So yeah. Just know that some computer programs write this as log and not ln. But most calculators, when you write log, mean log base 10. So good-o. And then e to the power of x, when you integrate it, is still e to the power of x. I think that's the whole list of your things. Oh, if it's not e, it's something else, right? If it's just, no, look at the... Yeah, okay. So there's one more on your list, which is this, some other number to the power of x. So powers, exponential functions other than e to the x behave the same way as e to the x does. It's still got an a to the x. But you have to divide by ln of a along the way, which works for e because ln of e is 1, and so it all works out fine. I think that's everything on your list. And if we were in another course, you'd learn things that have square roots, and you'd learn things that have cos and sine, and that'd be fun. Oh, that's okay. Square root is under the category of rewriting. So it's So that's fine. Square root is power of a half. So we're all good. Yeah. So this is your list of just do it's. And also on the list of just do it is you know that if you multiply anything by a constant, then that constant is still multiplied after you've done the integral. So if the integral of little f of x is big F of x, I'm just going to ignore the plus c's if that's okay. Then the integral of constant times, I'll call it k, times little f of x is that same constant times big F of x. That's how I think about it when I do it. But mostly you'll see it written in notes usually like this. That's another way of writing the same thing. It's useful to be able to do both. And I'll give an example of that. So this one's good when you're doing algebra and when you're doing integration by parts. This one's just how you do it without having to do lots of integral signs everywhere. Okay, and then also if you add two of them together, then you can do the integral separately. So if the integral of f is capital F, the integral g is capital G, then the integral of f plus g is capital F plus capital G. Same deal. I might as well write it down. If the integral of f of x, little f of x is capital of f of x, and the integral of little f g of x is capital G of x, then the integral of f of x plus g of x is capital F of x plus capital. So if you integrate first and then add, you get the same answer as if you add and then integrate. And then the short version of that is the integral of f plus g dx is the integral of f dx plus the integral of g dx. That's the short version of the same thing. Yeah. They both mean the same thing. It just feels different to me. So this one's useful for manipulating algebra expressions involving integrals. This one's useful for doing it. So this is everything in the just do it category. But I will add something to the just do it category in a bit. Okay. All right, here we go. Let's do some examples. Sorry, did you still want that? Here we go. Well, 3 divided by x is the same as 3 lots of 1 on x. 3 times 1 on x. And so the 3 is multiplied on, so it will still be there afterwards. And the integral of 1 over x is ln of x. Technically with an absolute value sign. I don't know if your lecturer has done it that way. Have they just done it with brackets? Just ordinary brackets? Okay. So just want to point out that that technically only works if x is a positive number, because you can't put in. He does? Okay. So I really should have changed this. This rule back here only works if x is positive, and if x is negative, you'll need to have the absolute value of x, which is just a very interesting magic trick. So, yeah. Okay, so ln of the absolute value of x. In many economic situations, x can't be negative because there's an amount of stuff. Like it's, number of things produced, and so it doesn't really matter. But for a probability density function situation, you are allowed to have negative numbers sometimes if it's a profit. And so, yeah, you've just got to be careful. Now, this minus 7 is multiplied on, so it will still be there. And the integral of e to the x is e to the x. And can I put a number here just to make it completely clear what's going on? This 8 is multiplied on, so it will still be multiplied on afterwards. And then I'll put the exponent up by 1, and I will divide by the new exponent. And then technically a nice plus c at the end. So what I've done to do this is I have used these 3 rules. and I've combined them with these rules, with the addition and stuff. So they're all on the just do it, and those things you're just allowed to write down the answer. And then you're supposed to simplify it, you know, if things cancel and stuff. Yeah. That's pretty much the just do it category. So there is one more thing to add to the just do it category, which is if the integral of f of x is capital F of x, if you knew that, technically plus c, if you know what your indefinite integral would be if there's an x, but you don't have an x and instead you have an ax plus b, then you'll just do what you would normally do for an x, and you'll divide by that number that's multiplied by the x. This is not listed explicitly in your notes, but most lecturers expect you to be able to do this without doing any working. I will do an example of it in a moment. The reason this works is because of the chain rule. If this differentiates to give this, then this will differentiate to give 1 on a times f of this times the derivative of this because of chain rule, and the derivative of that is a, and then it'll cancel out the 1 over a and produce this. So that's why. So lots of people call this the reverse chain rule. It always works. The problem happens if the derivative of the inside isn't a constant, you can't just divide by it. It's not going to work. That's what substitution is for. But if the derivative of the inside is a constant, you can just do what you would normally do and divide by that constant and it'll be fine. Yeah. So we'll do an example of that just to make that make more sense. Let's not put an e there. Let's do it as a 2. Right. Just so that I've actually used that rule along the way. All right, here we go. So this is 5 times 1 over thing. So the 5 will still be there. And 1 over 2x plus 3, I would know what to do if it was just an x. 1 over x would be ln of x. But it's not an x, it's a 2x plus 3. And so because it's 2x plus 3, I'll also have to divide by 2. So that's using this rule. I know what 1 over x becomes. It becomes ln of x. So 1 over 2x plus 3 will become ln of 2x plus 3, but I'll have to divide by the constant that's next to the x. And this, there's a 3 multiplied on, so it will still be there. I know what 2 to the x would become. It would become 2 to the x divided by ln of 2. But it's not an x, it's a 6x, so I'll have to also divide by that 6. You okay with what I'm doing there? So that's the classic. I don't know if you actually probably hasn't talked about it that way, but most lecturers who spend more than a week on integration expect you to just be able to do that. So just wanted to point it out. And so, I mean, you could probably simplify this a bit if you wanted. Not much. The 3 over 6 would become a half, and that's probably the best you can do. All right. That's the just do it category. So going back to my original list here, know your derivatives, and the reverse chain rule is the thing. They're both in the just do it. Yeah. well, technically there's the addition and multiplication, but nobody really seems to, they're not worried about that. You just do it. And so, yeah. Okay, the next technique is to rewrite it so that it looks like something in the just do it category. So if you're going to rewrite it, you know how I called technique just do it technique 0? Because it doesn't really count as a technique, you're just doing it. So technique 1 is rewrite it. And the classic is that you just have to, if you look at it and you notice that just some algebra would turn it into a thing that you know how to do, then do it. So the square root of x, for example, well, the square root of x is the same as x to the power of a half. And now that is a power of x. And there's a rule for that I can just do. I'll make the power go up by 1, and half plus 1 is 1 1/2, which is 3 halves. And then I'll divide by the new power. In a completely technical sense, that's what I'm doing. And when you divide by a fraction, it's the same as multiplying by the reciprocal. That's the right word, isn't it? So most people do this in one move, this thing here. I have just done it that way explicitly just to make sure. Yeah. That one. Well, if it was just an x, I would know what to do. That would be great. If that little x wasn't there, I could put the power up by 1 and divide by the new exponent up by 1, divide by the new exponent, and then because that's a constant times x plus 1, I could just divide by that constant. So I just want to, this is all the way, I just want to put it back here. X plus 1 squared all by itself. If that was just an x, I would know what to do. It would go up to cubed and I'd divide by the 3. But it's not an x, it's an x plus 1. And so I would divide by the constant derivative, which is 1, and so that's it. This is why this rule is so useful. But I've got an x in the way, so I'm not going to be able to just do that. So my only hope is to rewrite it. And the only way I know how to rewrite this is to expand it out. So my x plus 1 squared became x squared plus 2x plus 1. That's expanding using the perfect square. And then I multiplied all these by x, and now I'm here. And they're all powers of x, and so I can do those. The x cubed, I'll go up to 4 and divide by the new exponent. The 2 is still there because it's multiplied on. This will go up to 3, and I'll divide by the new one. And this is x to the 1 technically, so I'll go up to 1, 2, and divide by the new one. And if you really wanted to, you could write that as 2/3 all in one go if you were in the right frame of mind. I tend to make mistakes when there's fractions around, so I like to just do it carefully. Yeah. There's actually another way to rewrite this, which is not necessarily a good way, but I really want to show you because it's fun. What if it was this? What if instead of a 2 in that spot, it was a 20? Technically, you could expand that out, right? X to the 20 plus 20x plus 20 choose 2x squared plus 20 choose 3x cubed and so on. No, right? Watch this. It's so cool. If this had been an x plus 1, right, it'd be x plus 1 all to the 20, and I could have used that reverse chain rule on it. So why don't I just put the plus 1 in there, right? I can always add a 1 and take a 1, and it doesn't change what the thing is. It's the same function. And then look at this, x plus 1 times x plus 1 to the 20 is x plus 1 to the 21 and minus x plus 1 to the 20. How cool is that? And so I'll put this power up by 1, this exponent up to there, and I'll have to divide by the constant derivative, which is 1 anyway, so that's all right. And then I'll put this exponent up by 1 and divide by the new exponent. I have to divide by the derivative of that, which is 1 anyway, so that's fine. And ta-da, I have an answer. Isn't that fun? So, I mean, ultimately, it's basically rewrite as a power, expand, factorize. Any of those things is fine as methods of rewriting. The point of this technique is that if you look at it, sometimes you can do some algebra and turn it into something that's nicer. Yeah, this is one of my favorites. Big fan of that technique. Thoughts? Yeah? Yeah.
I think that's quite a lot.
Yeah. All right. So, and technically, actually, that rule for integrating a to the power of x is all. It could be done from rewriting if you didn't remember what that rule was. So, if you didn't remember the rule for integrating 2 to the x, you could go, well, that's 2 is the same as e to the power of ln of 2. Which is e to the power of ln 2 times x. And I know what the integral of e to the x is. It's e to the x. And it's not an x, it's an ln 2 times x. But because there's a constant multiplied by the x, I have to divide by that constant. Because ln 2 is just a number. It's like about 0.69. And look, this thing was originally 2 to the x. So if you didn't happen to remember the rule for integrating 2 to the x, but you did remember that 2 to the x with either the ln 2x, you could do this. Yeah. It's much easier to remember this rule, like if I'm honest. But if you don't remember, it's much easier to be able to go straight from there to there. That's the rule. But I just wanted to show you that it's often possible to figure out some of the missing ones if you don't already know. You cannot figure out 1 over x's integral from the other ones. It's literally the definition of ln x to a mathematician. Like, so you know how ln x is defined to be the inverse of e to the power of x? Like to cancel out the e to the power of x. Actually, mathematicians define ln x to be the integral of 1 over x, and then define e to the power of x to be the opposite of ln x. And that's because, what the hell does e to the power of 1, like root 2, even mean? It's a horrifyingly irrational number. How are you going to figure that out? But an area, like ln of 5, is the integral from 1 to 5 under 1 over x. It's an area. It's right there on the page. You can believe it exists. So anyway, one of my favorite things. Lots of maths is my favorite, you might have noticed. That's rewrite it. If we were doing trigonometry, then using a trigonometric identity to rewrite it as some other trig thing is one of those, is under that category, but we don't have that in this course, so we feel happier about that. Just pointing it out in case you ever do any ones that do use trigonometry. Because it technically could come up in some economic situations of something that oscillates back and forth. You can put a trig in there. All right, so technique 2 is substitution, which your lecturer calls change of variables. Doing okay? Sweet. Okay. Change of variables is designed to undo the chain rule properly. Like we've got a got a cheats version that works if the derivative of the inside is a constant. Just divide by that constant and it works. But if the derivative of the bit, you're looking at isn't a constant, then you're stuffed. So I'm just going to do an example. Okay. So this problem here is actually a bit of a psych. You can't use substitution for this one. But you would like to, right? There's if it was just an x plus 1, we'd know what to do. But it's not, it's an x squared. And the problem is that the derivative of this bit is 2x. And I can't just go dividing by 2x along the way, because if I did divide by 2x along the way, like if I did this naive, do not do this, but if I did this naively and went, all right, well, x squared plus 1 cubed and do this, and then I'll divide by the derivative of the inside. If I did that, then if that really was the answer, then differentiating this should produce that. But if I differentiate this, there's a 2x on the bottom, I'm going to have to use the quotient rule, and I'm going to get 6, you're going to get like an x squared on the bottom, and the top's going to be like crazy, and it's not going to come out to this. So it's just not going to work. You're only allowed to divide by that 2x if it's already there. Basically, that's the rule. And so when your lecturer writes this, and says that integral is crap. So if the integral of little f of x dx is capital F of x, then if there's a gx here and there's already the derivative of the inside and it's already there, then that will be capital F of gx. That's the rule. So if there had been, so therefore, x squared plus 1 squared dx. If there was already the 2x there, then I could go, okay, cool. If I ignore that bit, it's that thing squared, and that bit is the derivative of this. So it'll just disappear when I do the integral. Basically, that's the idea. And so this will become x squared plus 1 cubed 1/3 plus c, and that 2x will vanish because if I did it this way, it would appear. So I haven't technically done substitution there. I've literally done the chain rule in reverse. But that's got to be really rare, right? When the exact derivative of the inside happens to actually be exactly the thing that's there. That doesn't happen very often. I mean, to be fair, none of this happens very often in the actual life, right? But if you just randomly write a function down, it's not going to happen. And so we need something better than that. And so substitution is a method that allows us to still do the integral even if the exact derivative that we want isn't quite there. So it is designed for the situation when it's designed for a situation where there is a function inside another function, and you do need, and it won't work unless mostly the derivative is there. But it doesn't, it just doesn't have, as long as if it maybe not a 2x, but it's just an x or a 5x or a minus x, then that would work still. That's the basic idea behind it. If it's the derivative but off by a constant multiple, then it'll work. But sometimes it still works in other situations anyway. So just to point out though, this thing, since I can't do with substitution, I would expand it out. X to the 4 plus 2x squared plus 1, and I can do that. It's just, that's harder than it would have been this way. Okay. All right. So I will do, let me show you something. So technically it is possible to do this by expanding it out, and it's probably not that hard. So what I'm going to do is going to change the power to something that's a little harder to cope with. So with a squared there, I'd just expand it out, like just the quickest way. But with the 12 there, not going to expand it out. I'm really hoping this is going to work, so just bear with me. So there is an, all right, so here's the plan. Here's how to decide if the substitution is going to work. And the way to decide is to attempt to do it. First, you look to see if you could do it another way. And we go, well, we could expand, we could rewrite it, but that would just take forever, so we're not going to do that. So what we're going to do is we are going to call this thing that is on the inside U. Or G or T or theta or whatever you like, but U is the tradition. And we don't call it Y usually because it's normally Y equals something X. So, you know, Z's already reserved for three-dimensional geometry, and so U is the next available letter. Okay. And we know that the derivative of U is going to have to be there already in order for me to do this process. So I'm going to figure that out. Here's one of the tricks of this, is that even though du on dx is not a fraction, for the purposes of this, it works perfectly well to do this. In fact, in almost all situations, it is in fact okay to split up a derivative in that way. It almost always doesn't break anything. But this is useful actually, and this is getting at what substitution is doing to the graph of the function. Let me just, what substitution is doing to the graph of the function is you've got some wicked function. And this is all marked in terms of x. And whatever. If I said that u was equal to x squared plus 1, then each of these values of x would go with a different value of u. And so if x was 0, u would be, so these are my x's, these are my u's. U would be 1. If x was 1, u would be 1 squared plus 1, which is 2. If x was 2, u would be 2 squared plus 1, which is 5. If x was 3, u would be 3 squared plus 1, which is 10. If x was minus 1, it would be minus 1 squared plus 1, which is still 2. And so all the values of u work out to whatever they work out to be. Okay? So as I travel along this x-axis, then I can also imagine traveling along the values of u, right? But the values of u change faster than the values of x do. And so if I want to accumulate the values of the function, keep taking into account how much space they how much space they spend being that value, then if I'm tracking along the u's, a space of 1 in x actually counts for a big space of u's, because this gap of 1 x's is actually like 9 u's, and this gap of 1 x's is only 3 u's. And so what we're saying is that a gap of 1 u, that the speed that u moves as you move along the x-axis is twice the speed that x is using, and in fact twice whatever x you're up to speed that x is using. That's what that's talking about. Changes on the x-axis correspond to bigger changes on the u-axis. And if you're trying to take into account how much space you're spending being a particular value, you're going to have to sort of make the changes in u count for less so that it works out to the same area. That's the idea of what substitution is doing to the areas. If you listen to that and go, I get it, but I'm not 100% sure, that's fine. I'm still not 100% sure, but I do understand what this means. So, cool. Now that we're okay with believing that this works, I need to go looking for this in my function already. I don't know if this is how your lecturer does it, this is how I do it. And I can see an x dx in my function. If I pull one of these x's off the x cubed and attach it to that dx, then it will be here already. And so that x dx is worth half a du. And unfortunately, what I've got left is still an x squared left over, but that's okay. I can go back to here and rearrange this to get that u minus 1 is the same as x squared. So here we go. I don't know if you've been given problems like this in your course, but I'm hoping that it helps you make sense of how substitution works. So I'm going to remove one of those x cubes over to be attached to the dx, just so I can see what's going on. So x cubed, I can pull an x and an x squared. And now every piece of this has to be replaced with something involving u. I know that this bit is a half of du. I know that this bit is u. And I know that this bit is u minus 1. Nothing up. Okay, so here I am. I'm going to write it this way, even though I wouldn't normally do that. But so I have managed to change this function, this integral, to be, so we've got like a running total area of this function in terms of x, and this is our running total area of this function in terms of u. We've been very careful to keep track of how the speed that the u changes is related to the speed that the x changes, and that's all good. But what I've done is just turn it into another integral that I still don't know how to do. But that's okay. I just start again from the beginning of my list. Do I just know how to do this? No. Can I rewrite it? Yes, I could expand it out. U to the 12 times u is u to the power of 13. U to the 12 times minus 1 is u to the power of 12. And that integral, that I can do. So the half is multiplied on, so it will still be multiplied on afterwards. The u to the 13 will go up to the 14, I'll divide by the new exponent. This will go up to 13, I'll divide by the new exponent, and then there'll be a plus c. And so for the purposes of doing this integral, it's tradition, even though technically we know what u stands for, we feel unsatisfied if we started with x's and we finish with u's. So because we only created that u to help me do the problem, so I've got to put the x's back in. So the x is really, u is really x squared plus 1, wasn't it? Yeah. And I'd leave it there. I mean, you could multiply the half out and get like a 28 and a 26, but I can't be bothered. You could even factorize it if you wanted, but I also can't be bothered. What are your thoughts about what I just did? And the pieces that were involved? Okay, I'm just going to look back over it and find the bits. So the first thing I did was notice that I wasn't going to have a hope of expanding it out. And so I went, let's just hope that when I see something that's inside something else, so I'm going to call that u and hope that it works. So that's the first step. Choosing that I'm going to put a u, going to call a piece that's inside something a u. So that you said, how do you decide? You've got to have a function inside another function. And then the first thing you should do is figure out how the du is related to the dx. Like after you've figured this out, this is step 2. How is the du related to the dx? And you want to include as much as possible, as many x's as possible with the dx as you can, basically. And then if there's any x's left over, you're going to have to figure out go back to the original and try figuring out how to sub it in, basically. That was my secret third bit. So this was the first bit I did. Then I did this. And then this was my way of dealing with my leftover x's. And so in terms of doing it, I actually started, in my head, I was starting to replace pieces of it with u and going, oh crap, there's a bit left over. I'm going to have to replace that as well. You are allowed to do that, leave x's and u's in the formula at the same time, but it freaks me out when I do it. And so I like to just do it all in one go. But that was that step. So there's a step where you replace all the x's with something involving u. And if you haven't covered all the x's, you're going to have to go back to the very beginning of where you said what u was and rearrange that to sub it in. And then this bit is just integrating, this bit here. I have to go, now I've got a new integral, I'm going to have to start again and figure out how I'm going to do that. But if you've done a substitution properly, it shouldn't need substitution again. Like if you can do it with 2 substitutions, you should have been able to do it with just one bigger substitution. So that's usually a rule. And so I'm going, cool, I shouldn't use substitution. I should be using one of the earlier techniques, which is either just doing it or rewriting it. Does that look like something went ping there? Yeah. That's why it's so useful for me to have this list. Yeah. Okay, and then I did the integral, and then there was one last bit where I put the x's back in. So if you're extremely unlucky, then it's going to be quite difficult to put the x's back in because it won't look like what you started, but the kinds of functions that you have should be okay. If you were doing trigonometric things, then sometimes when you do the integral, you get to the end and you're going, that doesn't look like any of the things I started with. And I have to use some fabulous trigonometric identity to make it work. But we don't have to do any of that, so that's all right. Yeah. So can I just have a quick look at the notes from this one? Oh, that's your thing. I want the let's see if there's any substitution when he was doing the I'm going to do one of these examples. Actually, I'm going to do a slightly different example to these. I'm going to do that one. This is a classic. Okay, so I'm still going to do the whole thing. I'm going to look at this and go, do I know how to do this already? And the answer is no. If it was just ln x, I'd be good. If it was just 1 over x, I'd be good. But because they're divided by each other, it's not like there's a quotient rule for integration, so I'm just stuffed. And so it's not just do it. So the next thing after just do it is to rewrite it. I really don't have a hope. Like ln x can't be expanded or anything. Like it just doesn't interact with anything else. So I mean, I could, you know, I could be ln x times 1 over x, and then that would be like ln of x to the power of 1 over x. But what the hell is that? And so no, I can't rewrite it. It was worth a try though. So substitution is the go. And so I need to attempt to find a piece of this I'm going to call u so that the rest of it involves a derivative. But 1 over x is the derivative of ln x. That's really useful. So just remember that substitution in general is for a function inside another function. This has got 2 things inside it. It's got this and it's got this. Calling x equals u is just going to replace all the x's with u's. So I might as well just call u equals ln x and hope. But I also know that if I did go u equals ln x, then that would indeed have, I could rewrite it like this. And 1 over x is the derivative of ln x. And so I'm onto a winner with the substitution. So u equals ln x. So du on dx is 1 over x. And so du is 1 over x dx. And it's already there. I don't even have to adjust the numbers. It's just nice. So just want to be clear, if this had been, let me change it so it's harder, right? That had been an ln x over 2x. Okay, well, it's like the derivative, it's just off by a constant multiple, so it should still work. I'm going to still need to find a 1 over x dx in the formula. I don't have a 1 over x dx, I've got a 1 over 2x dx. So my choices are to split this up into a half times 1 over x, and that's probably the quickest way to do it. So I'm going to go, pardon me. And then I can do that. So just letting you know that if there's a, yep, oh yeah, just letting you know that if there's a constant that's wrong, you can usually fix it. And so ln x is u, half is still a half, 1 over x dx, all of that is du. Yay! So the integral of that, well, the half is multiplied on, so oh, damn it, I don't need the integral sign. Half is multiplied on, so it will still be there afterwards. And the integral of u is power exponent up by 1 divided by new exponent. And I really shouldn't have done that there. I need a whole new page. It's not going to fit. So there we go. Equals half is still there. U to the power of 2 divided by the new exponent. And so I've got a quarter of u squared, but the u is really ln of x. I would recommend not writing ln squared x. Just keep it with the brackets. Like, just leave it. That's good enough. Yeah, and it's not ln absolute value because the u wasn't originally ln with an absolute value, so we don't have to worry about that. Right, classic substitution. All right, I'm going to do a similar one. So can't rewrite that in a useful way, right? If it was an x plus 5, I might actually have a chance of rewriting it. Because I could do, oh, now I have to do it. This isn't substitution, this one, but I can actually do this one with substitution as well. It's probably easier. So I'll just run with this one. Just give me a minute. Okay. Can't rewrite it, the x squared. I can't factorize the bottom. It's just crazy. So I'm going to try substitution. And I'm looking at the bottom here. And if I did u equals that, I'd still have a u on the top and I'd still have like a u squared on the bottom, and it wouldn't be all that different. The numbers would be in different spots, but it's not going to work. So I'll try u equals the bottom. So I'm hoping you're hearing that a lot of the decision-making process is making a quick attempt in your head to see what would happen. If you do it often enough, then you can skip a lot of that reasoning. And so when a lecturer says, oh, you just have to do a lot of them and then you'll know, it's such a cop-out, because what you have to do when you're doing that is notice what things tend to go with what things, and you have to explicitly look. But it's nice to have some reasoning that can get you there a bit quicker. So my du on dx is 2x. And so my du is 2x dx. I can see in my formula, if I split it up, I do have an x dx. Because this is this times dx, and when you times by just a thing that's not a fraction, it ends up on the top. So I do actually have an x dx. What I don't have is a 2x dx, but that's okay. I can remove that. And what I really like is a 3x dx. That'd be even better. That's okay. I'll just multiply both of these by 3 as well. And now I have 3 on 2 du equals 3x dx. So I find it easier to set up as much as possible to be with the dx before I deal with anything else. And so now let's have a look at my integral. So it's a 1 over x squared plus 5 times 3x dx. If I'm going to be really explicit, you can skip that step. And the x squared plus 5 is a u, and the 3x dx is 3/2 of du. And so the 3/2 is multiplied on, so it will still be multiplied on afterwards. The u, 1 over u becomes ln of the absolute value of u, and the u is really x squared plus 5. How are you feeling? So this bit here. All right. That's an important thing to say. I'm going to see if I can pull out more so that you can see the decision-making process. So you're okay with this first bit where I got to here? Yeah. But then you're wondering, how do I deal with this bit? Okay. So my first, any x's that are part of this derivative thing here have to be found. That's the first thing that you need to know. So the fact that there's an x here that with the dx means that I'm going to have to find an x to attach to the dx. That's my first rule. And so I go looking to find an x attached to the dx, and there it is. So what I did notice is that what I don't have is I don't have the 2. So since I've found the x dx and the number's the wrong number, I'm going to move the number out the way and divide by 2. Now it's just this. That was my next decision-making process. I went, I have to find the x, and I've found the x, but what I don't have is the 2, so I'll remove it. That was how I made the decision. So I didn't think about this all in advance. I literally just one step at a time, find the x, crap, the number's the wrong number, I'll move the number out the way. So you can actually sub it in at this point. You can say, well, that x dx is a half, and just put it in. It's like a half of du, and you can just put it in. And there'll be a 3 here. So you could have done 3, there's an x dx, sorry, 3, and there's a 1 over x squared plus 5, and there's an x dx. That's how this thing is built. And then you'd have a 3, and that's a 1 over u, and that's a half of du, and that would have been fine. You could have done that. I just find that I tend to lose things if I do it that way. And I noticed, my first thing I noticed was that the 2 was the wrong number, and so I moved it out the way. And then I noticed, oh, there's a 3 that I could attach to this, so I will attach a 3. And that's how I made the decision to do that. It is extremely helpful to be able to rewrite things that are multiplied together and divided, like to be able to see a fraction like this and pull it apart as a 3x times a 1 over x squared plus 5. That's a really useful skill to be able to make it easier to do. I'm hoping that's helpful. If you want to talk more about it, we have a Maths Learning Centre open 10 a.m. to 4 p.m. Monday to Friday, all the way to the end of the exam period. Yeah, and if you want to be trying it in a place where you could ask someone if you feel stuck, then that's a good thing. Is that all right? I hope that's not too much of a cop-out. Okay. So substitution is actually really flexible. It's particularly good for things where you're not replaced. Like, you know how, yeah, so anyway, there's just this one back here that I did, x plus 1 to the 20, and I did that by rewriting. I could have done that with substitution as well. But the rewriting was fun. But I could have done u equals x plus 1, because the derivative of the x plus 1 is just 1, which means it is there. This is really naive. It's like I can't expand it out. Rewriting it is technically possible, but I didn't think of it today. And I noticed that there was something inside, and so I do substitution. And so I do this, and so I go, okay, so the x plus 1 is equal to u, so that's good. Go with that. The dx is equal to du, so that's good. And we're left with an x. So we'll do the same trick we did last time and rearrange this to get u minus 1 is equal to x. And I will literally, when I do this working, circle the bits and tick them, go, I've done this bit, crap, this bit's left. And so now every piece has a version involving u. And so I can go that x plus 1 to the 20 dx is, this x is over here, it's u minus 1. This x plus 1 is u. This dx is the same as du. And this is the same thing I had before when I did my other substitution thing. That you know, had the one with the x squared and the x squared on the inside and the outside. Yeah. So that's u to the 21 minus u to the 20. I'm favoring 20s today. I should have made it a 31 or something just to make it easier to notice that it was different. But the u is really x plus 1. And this is in fact the same answer I got by doing the rewriting process, interestingly. So I mean, technically substitution is just an extremely fancy way of rewriting things. It's a way of rewriting not just the bit next to the dx, but also the dx as well. So yeah, it's like rewriting and fancy rewriting. So I now have in my head, there's an episode of Friends where they have a competition to know who knows who better, and they say to you know, how many types of towels does Monica have? There's guest, fancy guest. So yeah, so yeah. Rewrite, fancy rewriting. Yeah. So I mean, this is just, the point is that you could use either method and they're both right, and whichever one occurs to you at the time is fine. And sometimes there is more than one way of doing it, and they're all okay. How are we feeling about substitution as a style? Yeah, but they all have the same bits, just to be sure. You choose something that's on the inside, you call it u, you deal with the du and the dx. Then you look to see if you've covered all the bits, and if there's anything left over, you rewrite. And then you sub it all in, and then you integrate, and then you put the x's back. So it always has those bits. There's a lot of them, but knowing that they're there is a useful thing. And this style that I've done of actually boxing the pieces is a useful way of making sense of written working. And it doesn't just apply to integration. If you're looking at anything in your course that seems complicated, going, what are the pieces, and just separate them, it'll make it easier for your brain to notice where one ends and the next begins. Yeah. Okay. Which leaves technique 3, which is integration by parts. So the chain rule is really trying to deal with, not chain rule, substitution is trying to do the chain rule backwards. And it's designed for things where there's a function inside a function. And we had that rule in differentiation. We had a rule for when there was functions inside functions. There was a product rule for differentiation, but for when there were two functions multiplied together. And integration by parts is the product rule, but for integration. It's designed for when there's two functions multiplied by each other. But it's just not as easy as the product rule because it's integration. Nothing's as easy as differentiation because we're trying to do it backwards. And it's like, so substitution in general has a function and then another bit next to it, and that bit happens to be the derivative of the inside, and then it all works. And it's flexible enough to be able to cover more things than that, but in general, it's got two bits multiplied together. So if you've got two bits multiplied together and one bit isn't the derivative of the other, then that's what integration by parts is for. But you have to imagine that one of the bits is a derivative of something. So when you see two things multiplied together, which I shall call U and V, what you have to imagine is that one of those is already the derivative of something else. So you look at it and say, that's the derivative of e to the x. And so what you're going to do is not call it v, but call it v dash, because it's already their derivative. And then this thing becomes two pieces, or if you like, two parts, which is why it's called integration by parts. And so the first part is u times v, and so the v dashed has vanished. And so that's an integral. An integral has happened when you did that because the v dash has become a v. And the second part, it's still a v, but the u has become a u dashed now. So we did an integral, which is why there's no integral left here. But then we did a derivative, which means we're going to have to do an integral to undo the derivative. And that's why there's an integral back again. Basically the idea. Like this is the integral that involves a derivative. This is just plain functions because an integral involving a derivative would sort of cancel each other out. And this is a different integral involving a derivative. The purpose of it is that hopefully by the time you get here, even though the v in general will be more complicated after you've integrated it, the u will be simpler after you've differentiated it. And if you're very lucky, the u will vanish entirely. If it's just an x, then when you do the derivative, it'll become a 1. And hopefully by that point, now it'll just be one thing and I'll know what to do. I will point out to you that it doesn't actually matter which one has the dash as long as the other one has the dash at the other end. So it could just as easily be this one has a dash here and the other one has a dash here. It doesn't matter which one is which, as long as it changes which one it is as you get to the other end, which is what your lecturer is probably talking about with the switching. But I have no idea really. No, I actually have no idea what he's talking about. Oh, that is so unhelpful. It only works because it's e to the x and the derivative of e to the x is e to the x. Oh, just, oh, beware of the toast. Oh gosh, sorry. Beware of the toast means be careful because anything that appears in a list of examples, people will assume is the truth, even if it's just a coincidence that it's there. And so because this example, the derivative of e to the x is e to the x, you can just switch them, but no other function does that. And so this is the only example we have. And so you assume that switching is a thing you can always do, but you can only do it in this situation. Okay. I'm okay. I'm okay. Okay, so I deliberately write it this way because that's how it turns up when I do it in actual working. And it goes from being two things multiplied to two sets of two things multiplied. So overall, it looks more complicated, but the idea is to turn something that was impossible into something that was possible. And just like substitution, it doesn't actually give you the final answer. It just gives you something that you then still have to integrate to get the final answer. Right. And just like substitution, it tends to go with things that are multiplied together. But it's in the situation where you can't find the derivative of one bit in the other bit. I'm going to do this one again, but by yet another different method. Substitution is probably the easiest of the three methods to do this one, but I just want to point out that it's possible. I would not do this by parts, but I'm just pointing out it's possible. So I'm going to assume that this is made of two pieces. And it's going to become, when I'm finished, two pieces that both involve two pieces. So when I do integration by parts, I always write this down first. And then off the side, I write down what the u and the v is. And so I have to now choose which one's going to have the dash and which one doesn't. And so I know that if I differentiate an x, it will disappear. And so I'm going to call that one's going to get differentiated at the end. And so the other one has to be a derivative at the beginning. That's how I made the decision. So there's two decisions. One is, will it get easier if I differentiate this? And the other one is, if it doesn't make any difference, which one do I actually know how to integrate? Because you can't choose the one to be v dash if you don't know how to integrate it. So that means that we can now say that u is equal to x, which means that u dashed must be 1. And we can also say that v dashed is equal to x plus 1 to the 20, which means that v is the integral of that, which means it must be x plus 1 to the 21 divided by 21, because you put the exponent up and you divide by the new exponent. So this was a derivative, and this was an integral. Yeah. Some people, on some days, if I'm in a real bad mood, I will sometimes write it this way. And I'll write it v dashed at the bottom, which is the thing I started with. And then I'll go up to figure out what v is. This is fairly stupid, but the reason is that in my head, integration is up and differentiation is down. So it doesn't really make any difference. I just wanted to point out that that's something that you might see if you watch some of my other seminars. But some people, it really helps them to have this idea that integration is up and differentiation is down. And if they organize everything that way, it's a little easier to process. Okay, so now I have on the side written down what everything is. I can sub it in. U is x. V is 1 over 21 times x plus 1 to the power of 21 minus integral. U dashed is 1 and v is 1 over 21 x plus 1 to the power of 21 dx. Okay, so and this integral, that's just a number, so I can just do it now. The 1 over 21 is still there. The exponent will go up to 22, and I'll divide by the new exponent. And the derivative of that is just 1, and so dividing by 1 isn't going to make a difference, and I'm done. And this looks thoroughly different to the answer we had before, but algebraically it's the same, possibly off by a constant at the end. So if I expand this all out, I'll get exactly the same thing if I had expanded out the other one, but I might possibly have like a 1 or a 2 or something wrong at the end, but that's okay. That's all part of the plus C. So how do you feel about the process of doing integration by parts via this example? So I will do the one that was in the notes. So my function here, there is absolutely no chance of rewriting that because exponent, x in the power, x up here in the exponent and x down in the base, they're just not going to interact together very well. So that's sad. Substitution is not going to work either because there's nothing inside other stuff. Like, you know, I could do u equals x squared, but then this would have to be a root x and that would just be worse. So no, it's not going to help. So integration by parts is the go. All right. Can I just make it just even a little harder? No, I'll just do this one. I'll just do this one. Okay. So I'm going to call these two pieces u and v, and they're multiplied together, and they will become uv minus the integral of uv dx. But I still have to put my dashes in. Okay. So I have to know that it's going to get simpler when I differentiate it, the thing that doesn't have the dash. And e to the x is not going to change at all when I differentiate it. So I can't put the dash, I can't get, this can't be the one that ends up with the dash at the end. This one's going to have to be differentiated when I get to the end. Because even though it's not going to go away, the e to the x is just not going to change at all. So there's my decision. U is x squared according to this, which means that u dashed is 2x. And then separately, the v dashed is x e to the x. And so the v is also e to the x. So I started with these, and then I figured out the other ones. So a lot of people do like to write it in this little grid here as well. Okay, so that's the information I have chosen. And so therefore the u is x squared. The v is e to the x. The u dashed is 2x. And the v is still e to the x. And here I am here. And oh dear, it's still not something I know how to do. But this is what you're supposed to do. You're supposed to look at it and go, do I know how to do that? No, rewriting is not going to work. Substitution is still not going to work. Integration by parts. Let's do another one. All right. So this is going to be x squared e to the x minus the integral of, I've already used u and v, so technically I should use the different letters because I've already used those letters. It is okay to use u and v again, but technically it's confusing from a maths point of view. I will call them f and g just to... And so this thing here will be replaced by a new thing, which is fg minus the integral of fg dx. How are you feeling about what just happened there? Yeah. So I have to choose which one is going to be differentiated and which one's going to be integrated. That f, that 2x there, if it gets differentiated, it will end up being just a number 2, and I can deal with that. So this is going to be the dash here, and that's going to be the dash there. All right, so write that down. F is 2x, and f dashed is just 2. That went down. And then we also know that g dashed is e to the x, and so g is still e to the x. All right. So we have that is x squared e to the x minus big bracket f, which is 2x, g, which is e to the x, minus the integral of f dashed, which is 2g, which is e to the x dx. And I'm almost there. And the integral of 2e to the x I can do. The 2 is a constant, it'll still be there. And the integral of e to the x is e to the x. And so I'm done. And now that the integral signs are all gone, I'll whack a big plus c on the end. And I don't like brackets with stuff. I could expand that out, this minus and that minus, make a plus. How does that feel? easier to follow than, yeah. I don't do integration by parts enough to be able to do that without writing down the F's and the G's and the U's and the V's. And so I think it's nice to have that little bit of extra support. And when you do substitution, you write down the U's. So why not do it now? Yeah. And so you can imagine if I had x cubed, then you would have to do it 3 times. And so if you do have something that's a big power, what you normally do is create a formula for what it's going to do in terms of what the power is, and they call that a reduction formula. So it's technically possible, but I don't think your lecturer has shown it. But it's they do this sort of thing where you go, what is the integral of x to the power of n e to the x? Because we've already done it twice, and they do that. And so you can just do it as a formula. So this is a classic, I mean, your lecturer could ask this question. Find a formula for what this is in terms of n. And so you would go, that's okay, I can do this. I know that it's u v dx. Can I make, I'm going to put the 2x, no, I'm just going to leave it. Just going to leave it. And I know that if this n was 3, then it would get lower when I differentiate it. But also the e to the x isn't going to change, so that's just going to be bad. And if I integrated this one, it would just get a higher and higher power, and that'd just be bad. And so my u would be x to the n. And so my u dash would be n lots of x to the n minus 1. No. That became this, and my v dashed was e to the x, and my v became e to the x. Okay. Really should have left space for that. And so my u is x to the n, and my v is e to the x. My u dashed is n lots of x to the n minus 1, and my v is still e to the x dx. And so there, that's the formula. Like that. I can bring this n out of the brackets. I haven't actually used that rule at any point yet, but I can use it now. Yeah. So watch this. Ready? Ready? So therefore, according to this formula, the integral of x e to the x dx should be x. So this is x to the 1, right? X to the 1 e to the x minus 1 integral x to the 0 e to the x dx, which is x e to the x minus 1, and x to the 0 is 1, and the integral of e to the x is e to the x. And so I'm good. And the integral of x squared e to the x is x squared e to the x, because the n is 2, minus 2 lots of the integral of x1 e to the x, because 2 minus 1 is 1. And I already have a formula for that. I've just wrote it down. And so I can just straight up sub it in. And if I want x cubed, I can go, oh, that'll tell me what it is in terms of x squared. And I just wrote down a formula for the x squared, so I can sub that in. And so you're using it in the opposite direction. And it's just, I appreciate it. And it reminds me of Harry McClary, like you say, because, you know, when you got x cubed, it uses the x squared and the x to the 1. You've got x to the 4, it uses x cubed and x squared and x to the 1. It's like Harry McClary from Donaldson's Dairy. Hercules Morse as big as a horse, and Harry McClary from Donaldson's Dairy. And Muffin McClay like a bundle of hay, and Hercules Morse was as big as a horse, and Harry McClary from Donaldson's Dairy. This is just what it reminds me of. So, yeah. So that's not that important, but it's not that different from just doing straight up integration by parts. So you are allowed to do it even if you don't know what this number is. Yeah, and that's what integration by parts is particularly useful for creating ways of doing things that you're going to have to repeat over and over. But it's also just useful for products, because that's what it's for. Yeah. Ooh. And if we're using sine and cos, then sometimes when you do integration by parts twice, you end up exactly back where you started, and the world is sad. But you usually end up back where you started, but with a different number than you started with. And so you can go, well, I've got 1 here and there's 2 of them here. So if I put that over there, it'll be minus 1 of those. And it's just the coolest stuff. Like, integration techniques, like one could argue in the modern world where we have things like Wolfram Alpha, integration by hand with formulas is probably not a useful skill, but sometimes it's nice to just feel like you can be good at something. And that's what I like about integration. So that's the rules. So if I just put like a random function, like I have no idea if this is even possible. But I just thought I'd try it. Yeah, probably not possible, but you know. Yeah, no idea, but let's give it a go. I don't know how to do that already. And I could supposedly rewrite it a bit. Maybe. If that x up there was an x plus 1, then it would cancel with the x plus 1 at the bottom, and I might have something prettier. But nah, it's just, I've chosen a bad one. I'm sorry. Or you could do substitution, call that u. And then it would be just a u on the bottom instead of an x plus 1 on the bottom. Let's try that. The rewriting just sounds like it's just going to get worse. So I'll try the u equals 1. Then du on dx is 1. So du is equal to dx. Okay. And so we've dealt with the dx, that's du. And we've dealt with the x plus 1, that's u. And so we'll have to deal with this x and this x. So let's see, u minus 1 equals x. So that deals with both of them. So this x becomes u minus 1, and this x becomes u minus 1, and this x plus 1 becomes u, and this dx becomes du. And then at the very least, I've got u divided by u is 1, and 1 divided by u. And that's not too bad. Because I can totally do this now, right? Because that's like e to the u minus 1 plus. And I can at least do that bit. That bit I can do. The other bit, not so much. But that looks much more squarely like it's a part by parts sort of thing, because it's 2 bits multiplied together. So that's what I would attempt, to do it by parts. It's not going to get any better. But yeah, that's going to turn to crap. Because like when you integrate this, you'll get ln. And so I'll then have to integrate ln u times e to the u minus 1. And it's like, that's just worse. And if I differentiate this, I'll have e to the u divided by u squared, and that's also worse. So no matter which one I choose to be the one I integrate and differentiate, it will just still not work. And so, crap, this is bad. I will choose not to do this one. Okay, worth a try. Right. They won't, your lecturer, if they're concentrating when they write their exam, will not give you one like this. It was worth a try. Like, I just wanted to show you my decision-making process about whether I was going to be able to do it. And at least if this did turn up in the exam, I've gotten to a point where at least part of it I know what to do. So, yeah. Yeah, actually, I know that this is not actually possible. But I'd have to use infinite series to do that one. Did you do series in this course? Yeah. So because e to the x is 1 plus x squared over 2 plus x cubed over 3, 6 plus, yeah, there's a power series for it. So, yeah, anyway, no. I hate coming up with ones that, oh, have I really used all the paper? Not quite. This is the point at which you try to come up with things that you're going to be able to do. And coming up with random examples is a useful thing. They're the techniques of integration. I'll show you something. Yeah, we'll go from 0 to 1. Okay. Yeah. So it's not substitution is not going to really help that much. It'll just turn it into something that's still two things multiplied together. I already skipped the just doing it and the rewriting because look at it. And so, so I'm going to do integration by parts. So I'm going to call this the integral from all right, there is something missing here. See how this one had numbers on it? This is going to have numbers on it as well. But this is what happens after you've done the integral. So it will have numbers on it like that. This is a definite integral integration by parts. Yeah, that's just, I was just excited to show you that. I know I'm going over time, but I just want to wrap it up. So I'm feeling better about this. So let's see. If I differentiate that, it'll become 1, and so it'll disappear. So I'll put the dash there. So u is x plus 1, and the u dash becomes 1. And the v is e to the 2x. Oh dear. E to the 2x is not just e to the 2x. It is e to the 2x divided by 2. So, as I said, beware of the toast. I wanted to make sure there was an integration by parts where the e to the x changed because it wasn't just e to the x. That was important to me. So my u is x plus 1. My v is a half of e to the 2x, and that's going from 0 to 1. And then I've got integral from 0 to 1 of u dashed, which is 1. And my v is a half of e to the 2x. For the purposes of this, it's actually really useful to be able to do this trick when you have an answer after a definite integral. You can pull constants out of this and times by that at the end. So sometimes that's useful. That half came out. I just wanted to show you it's a thing you can do because I don't really feel like having lots of halves. All right, and this integral, half is already there, so it'll still be there afterwards. And then the e to the 2x will go up to e to the 2x, and then I'll have to divide by that 2 because of that reverse chain rule. Okay, so I've got a half of and so I'll sub it in, see what I get. So I've got a half of 0 plus 1 e to the power of 2 times, no, that's the wrong end, David. 1 plus 1, 2 times 1, minus 0 plus 1 e to the 2 times 0, minus a quarter of e to the 2 times 1 minus e to the 2 times 0. And that becomes a half of 2e squared minus 1 times, and e to the 0 is 1. And we've got e squared minus 1 again. All right, I suppose I should expand it out now. I have to deal with the fractions. I thought it was worth a try. So I've got a half times 2 is just e squared minus a half minus a quarter of e squared plus a quarter. And so I've got 3/4 of e squared minus a half plus a quarter. If I go down a half and up a quarter, then there's a quarter left to go. Like a quarter is half of a half. Yeah, a half minus a quarter is a quarter, but it's minus a half plus a quarter, so it's minus a quarter. That's the answer, which if I had a calculator, I could figure out. So that was just an example of definite integral integration by parts. There is actually definite integral substitution as well, in case you're interested, but I don't want to do that right now. So if you do want to do a definite integral substitution, did your lecturer, let me just look. Should I do a definite integral substitution just to round it out? Let's do it, just to go back and fill in one of the definite integral substitutions. Just give me a sec. I'm just going to make it easy on myself so that the answers work out to nice whole numbers, which doesn't always happen, but I would feel better about it. So. All right, there it is. The integral from 0 to 4 of x times root of x squared plus 9 dx. Okay, so I can definitely not expand out a square root. They do not behave that way. They do not interact with plus that way, so can't do that. Rewriting, well, if there was an x squared there, then I could probably do that same trick of like doing the plus 9 minus 9, and that would have worked, but I would still have an x squared plus 9 underneath, and I'd have to deal with that somehow. And so I reckon substitution is the go. Just for my own purposes, it's much easier to run through the whole process every time. So u is x squared plus 9. And just a second. I'm going to put a 10 there. Just want to make it even harder. Okay, so du on dx is 2x. That's fine. And then du is 2x dx. So I have committed to doing this x squared plus 9. It's not too late to change it. I can always cross it out and go back, but it's working. So this bit is u, so that's good. I can see an x dx here. But the formula I've got at the moment says 2x dx, and I'd really prefer it to be a 10x dx. So times by 5, that'll do it. And so now my 10x dx can be replaced with a 5 du. Now, are you ready for the secret? Well, it's not secret at all, for the magic trick. So you know how I said you have to replace all the x's with u's, right? This isn't actually just a 0. It's a x equals 0. It's a value of x that I have to put in. And so I have to replace that with the matching value of u. And this isn't an x. This isn't just a 4, it's an x equals 4. So I now have to go, this x equals 0, what does that mean u has to be? Well, u would have to be 0 squared plus 9, which is 9. And this x equals 4, that means that u would have to be 4 squared plus 9, which is 16 plus 9, which is 25. Oh, look, it's a square number. So that's good. It's almost as if I planned it that way. So that's the secret trick to making indefinite integral substitution work. So now every piece of this I now know what to do with. So I'm just going to write it out again so it's all on the screen at the same time. And I'm just going to... Okay, so one piece at a time. Here we go. The x equals 0 gets replaced with and u equals 9. The x equals 4 gets replaced with a u equals 25. The 10x dx is a 5 du. And the root is still a root, and the x squared plus 9 is a u. And now here I am. Okay, all the way back to the beginning. Do I know how to do this? Probably not quite, but I know how to rewrite it as a power, so I could do it that way. So now that all the x's are gone, I can leave the u equals as out of it. Just that you know, it is technically possible to not change these and just keep them as x equals all the way along and go from x, this integral of u from x equals this to x equals this, all the way until you get to the end, and then put the x's back in, and then you can sub the numbers in if you wanted. Yeah, just as a, but I don't because it's easier to do this. So now that everything's in terms of u, I can get rid of that. And so this is u to the power of a half. And the integral of that, all right, so it's going to be from 9 to 25. The 5 is multiplied on, so it's still there. The u to the half will go up to u to the 1 1/2. And so that's 3 over 2. And I'll divide by the 3 over 2, which will make the same as multiplying by 2/3. So I've got 10/3 of u to the 3 over 2. All right. Sure, David. So I guess I could pull that 10/3 out, couldn't I? I reckon that's going to make my life ever so slightly easier. So all these plain numbers can come out of these brackets. The reason is there's a subtraction and both of those pieces have that number, and so I can factorize. Right. Okay, so I've got 10/3 of 25 to the 3 over 2 minus 9 to the 3 over 2. Now, 3 over 2 is the same as to the power of a half and then to the power of 3. So just for the long version of it, this is 25 to the half, then to the 3, if you really want to do it that way. And 25 to the half is the square root of 25, which is 5. And 5 to the power of 3 is 125. And 9 to the power of a half is the square root of 9, which is 3. And 3 cubed is 27. So 10/3 of, what's that? 98, which is nothing pretty. So 980 on 3. It's a perfectly good number. So there was some new arithmetic stuff here that was of interest with the 3 halves behaving this way. And that's why I set it up so that my numbers are square numbers so that I could square root them. This 25 to the half is 5, which is a nice whole number. Otherwise, you just have to leave it like that and do like calculator or something. Are you allowed a calculator in your exam? Oh, good. Sometimes it's easier because then if you didn't have a calculator, you totally just stop there. Well, it is the answer. Yeah, so that's substitution definite integral, and it is slightly shorter than finding the indefinite integral using x's and then subbing in the x's, because you don't have to put the x's back because you change the limits into value, just numbers. And so it's just a little bit shorter. I mean, technically you're still doing the same work because you did the calculation here, but it just feels shorter. Yeah. Well, there you go. That's integration. I hope that was helpful. Thanks for watching. Good luck.